All right, let's get started. Today we have a special guest from Amazon Robotics, Aaron Parness. I actually knew Aaron since 2003. Aaron is actually our MIT mechanical engineering alumni. He'll turn on the mic, maybe.
Yep.
And I still remember when he first joined the Mark Kokoski's lab, Stanford. He was so happy getting out of the East Coast weather, joining Palo Alto blue sky. I was like, oh my God. And so he spent a couple of years, and Aaron graduated and joined JPL and worked on this amazing climbing machine with the claws, and we kind of worked on similar thing at Mark's lab. But now he's leading a huge lab in Amazon Robotics. So we're gonna see a lot of cool stuff today in real world, because one of the motivation to invite him was like, gosh, we need to show what the real world robotics look like. Stop seeing these like toy examples. So he's gonna show something very close to real, right? Like,
Yeah.
All right. So thanks for coming here, and then I will take it away.
Yeah. Thanks very much. It's really been, my pleasure to be back on campus. I was course 2 undergrad here, and I think 2007 is really the course that set the hook in me and made me want to be a roboticist. And I actually took Harry Asada's Intro to Robotics, believe it or not, 20-something plus years ago. And so, it's familiar and also foreign. It's changed a lot, but it's great to be here. As Songbei mentioned, after MIT, I went to Stanford and then to JPL, and I really focused on climbing robots and robots for getting to very extreme terrains. So the analogy I used to use is, we send the Mars rovers to the Grand Canyon, but they only get to drive around in the parking lot. And I wanted those robots to go down and look at all the layers and climb around. And I had a ton of fun doing this. I got to go to lots of places and deploy the robots to test them in extreme environments on Earth. And if you are interested in this, I did give a Robotics Institute seminar at Carnegie Mellon right before I left JPL. That's online in like 2019. So I will refer you to that and talk about something else that I find has been surprisingly fascinating. And that's e-commerce fulfillment. So how we get the stuff you order on Amazon.com to you, and how that process goes right. And this is one of our warehouses. And so I'll kind of give you a high-level overview of the process. These are huge buildings, up to 1 million square feet. There's thousands of workers that are in each one of these buildings, and actually thousands of robots. But if you really try and boil it down, there's a kind of a flow that happens. So trucks come into the docks with inventory, stuff. We need to get that stuff off the trucks and store it somewhere. Once it's stored, we store it in these fabric bookshelves. You'll hear me call them pods. Once it's stored there, it's available for sale on Amazon.com. And it will sit there for a few minutes, maybe a few days, even a few months sometimes, before someone clicks the buy button. And the algorithm says we should fulfill this order from this particular warehouse. Once it's been bought, one of these pods will go to a station. Someone will pick the item that you've ordered. And if you've ordered multiple items, we need to accumulate those all together. And then we'll pack them into hopefully the smallest and most environmentally friendly package that we can use. And in some cases, that means no package at all. So I've been buying a lot of diapers lately, and they just come with the label straight on the outside of the box. That's the greenest way to ship, is not to use a packaging at all. Once those orders are packed, we need to sort them. Because these buildings are serving millions of items, they don't all come to MIT campus. Some of them might go up the street or to some of those other places. And so there's a sortation step. And then they go back onto trucks and out the building. And so at a high level, this is kind of what it looks like. This is a simplification, but it is one of these sort of system of systems. And so if we're going to apply automation, you can either rethink the whole thing, or you can try and surgically insert robotics where it makes sense and claim partial credit as we go. And that's a little bit what my team is doing. Just to touch on the scale, there's hundreds of these warehouses. And as I mentioned, each of them has thousands of workers of both the robotic and human variety. In a given warehouse, you might have up to 20 million items, maybe 1 million unique items. So this is one of the big challenges for Amazon is we sell everything. So it's not just a grocery store which might have 40 or 50,000 SKUs. We're talking about an order of magnitude or 2 orders of magnitude above that. Those bookshelves, those fabric pods, there's tens of thousands of those that are moved around by those thousands of Kiva robots. And then per day, this network is producing tens of millions of packages. In peak around the holidays, that'll go up even over 100 million packages that will go out on Black Friday or something like this. So huge scale. That's both a challenge and an opportunity. So Amazon is sort of uniquely positioned because we have internet scale data of robots doing manipulation tasks. And there's not other places in the world that have this kind of data. And so we can certainly leverage that for some of the latest techniques that you see coming out to try and train our systems or train our perception algorithms to perform better. I'm going to zoom in on the storage aspect. So one of my teams, my biggest project, we're working on Stow. So this is taking inventory and putting it onto those fabric bookshelves. And so here you see those Kiva robots. Kiva was founded, it's just up the street in North Reading. I think we have a tight alliance with MIT. We're sponsoring, I think, this seminar even. So unrelated to my being here, I swear. But the Stow aspect here, I'll show you another video, has a couple of steps. You'll see there's a new pod will arrive. The person needs to scan and see where might there be available space. And they have an array of items, maybe 50 to 100 items in 5 or 6 totes that they can choose from. Once they pick where that item will go, they need to manipulate these elastic bands. So there's essentially rubber bands in front of the bin so that stuff doesn't fall off the shelves as those Kiva robots are driving around. There's also a fabric bin lip right at the bottom of that bookshelf to make sure, again, stuff is not falling out. It's a large workspace. So there's a ladder so that you can reach the top rows, and you have to crouch down if you want to store stuff in the bottom that's down at your ankles. You need to play this matching game, right? And so if you go try this, it's actually surprisingly challenging. You think, OK, I have this toaster. It's going to fit in this spot. And then you go and you push and you shove, and it just doesn't fit. And that, of course, slows you down quite a lot if you're doing this task. So if we want to automate this, if we want a robot to do this task, let's deconstruct it into the sort of component steps. First of all, you need to perceive and decide, what item is going into which bin and what kind of motion are you going to use to put it there. You need to get those elastic bands out of the way. You need to grasp the item, make space in the bin. I commonly say this is not a peg and hole problem because we don't need to just identify the holes. We need to make the holes. So you need to manipulate items that are already on those shelves in order to maximize the space that's available. And then finally, you can stow the item. You place the item on the bookshelf. So in this perception piece, we do have some advantages. We know, at least with as good as our data is, what the items are that are already stowed in those bins. We know their dimensions and their weight. Although I will tell you this data is not reliable. A lot of times our sellers are putting this data in. Maybe they confuse inches with centimeters, ounces with pounds. If you pull down all the data, you will find some of these bins are over 1,000,000% full because they gave a gift card a 1/4 inch thick volume, and then you have 500 gift cards in the bin. So don't count on that data to be perfect, but we have some of it. We can open those elastic bands to make space. Grasping the item here, I'll show you more on this later, but we've chosen a parallel plate grasper. This sort of simplifies getting the item into the hand, simplifies grasp planning. It also gives you 6 degrees of freedom pose control of the item, which is important for us. To make space in the bin, we have another sort of simplification on the hardware side. We use a piece of sheet metal. We call it a bin manipulator or a blade, and we use that to push items or rotate items. But we're not trying to do very complex things. We're trying to use a simple piece of hardware that's going to be reliable, day in, day out for 7 years. And then to stow the item, rather than putting the hand all the way into the bin and taking up a lot of valuable space, what we do is we actually put conveyor belts onto those paddles. And so you maintain that 6 degree of freedom pose control of the item all the way from grasp into its final location. So we can kind of spit the item into the space. So what do we care about as we do this task? We care about rate. So how fast can you go? We need to do hundreds of units per hour. We care about eligibility. This is like the variety of items you can use. MTBH is we call it material to be handled, but it basically means I can do the makeup, the teddy bear, the bowling ball, the light bulb, the sweatpants, the iPhone, all of the stuff that you might buy. Fullness. Fullness is really important. This is gross cubic utilization. If you only put one item in each of those shelves, you would need a lot more warehouses. We want to put our warehouses close to our customers, which means New York City, Tokyo, Boston, and 1 million square feet in central Tokyo is a very expensive warehouse. So we really need to fill up those bookshelves as densely as we can. And then there are 2 headwinds. These are defects. So damage is obviously when you break something, or amnesty is what we call when an item falls out of the bin. And it can either fall out at the station, or sometimes worse, it's kind of hanging out, and then the Kiva robot drives it back out into the storage floor, and it falls out somewhere where you don't know where it is. We are very sensitive to these defects. So each time you stow an item, maybe 10 cents, 20 cents, 5 cents, depends on the process. Each time you break an iPhone is, $500, $600, $700. And so if you break a high-value item, the robot has to operate for 2 whole days before you start making money again. If you pop open a Gatorade bottle, you make a mess, the robot now is down, while somebody's cleaning it up for several hours. This is also very, very expensive. And so this is some of the reliability pieces that Songbei kind of mentioned. We count our damage rates in a metric called DPMO, defects per million opportunities. And that may seem like a lot, but we're picking 1 million items a day. And so this is happening every day, even if you only have 1 DPMO. And so we don't have 1, by the way. It's way higher than 1, don't worry. But 95% is not good enough, right? We need to be, much better than that. So this is kind of the teaser video. The marketing team made this one, so it's more about flashiness than actual content. But you can see we've got a 6 degree of freedom robot arm. It rides on a 7th and 8th axis gantry so that it can reach both the top shelf and the bottom shelf while having high manipulability. We don't want to be near singularity when we're trying to do force in the loop kind of control. You see our older version of the band separation here. And you see that sheet metal blade that's used to push items and manipulate things. And then we spit the, whatever that was, ping pong balls or something, into the bin. So why has nobody done this before? Amazon's been in this business for a while now. What makes this problem hard? There's kind of 2 main advances, I would say. Previous robots haven't used force and torque in the control loop, and so they're not able to handle the high contact. They're not able to move those items around, make space, deal with inadvertent and unexpected loads. Second one is that they haven't had the level of decision making and reasoning that we have today. And here we're not doing as much invention as just riding the tailwinds of AI and machine learning to make better decisions and have higher fidelity, world models and depth models of the system. If you think back and think about industrial robots now, they were not built for the warehouse. They were built for the factory. And so you've probably heard the term dull, dirty, and dangerous. These robots are doing things like welding and fixturing, inspection, tasks that require high stiffness and high positional accuracy. And so the robots are only controlled using their positions in space and the derivatives, right? Velocity, acceleration, jerk. And that makes them useful for a lot of tasks in the factory. But if one of these robots runs into something or makes a collision, it either emergency stops or it just smashes through the thing and keeps going because it doesn't have any sensor to know that it actually hit something. So I affectionately call these older style of robots numb and dumb, because they don't feel and they don't think. This is very different, of course, than how we manipulate our environment. We have sensors all over our hands to feel contact, and in our muscles to detect forces. This is Roland Johansson's work. It's from about 30 or 40 years ago, which is why the video is so grainy. But he's numbed the subject's hands to show just how important those sensors are for dexterity. And I challenge you all, you can do this experiment yourself. The next time you're in a Boston snowstorm, you take off your gloves, you wait 1 minute, and then you try and tie your shoe. The other thing we do as humans is we plan for contact. So to pick up the coin, you actually touch the table. You don't touch the coin. You touch the table and slide your fingers until you achieve the grasp. Same is true turning the page in the book. You're not planning a millimeter precise pinch grasp. You're moving to contact and regulating the force as you slide your finger so you don't rip the page or hurt your finger. DARPA realized that this was an important sort of advance in robotics, maybe 15 or so years ago. I was at JPL, and they funded the Autonomous Robotic Manipulation Challenge. And in fact, both my hardware tech lead on my team, Kurt Salisbury, and my science tech lead, Nick Hudson, both came from winning teams in this competition. You see the robot doing things like making contact with the table before proceeding to the next motion in the sequence, or you see it wiggling in order to get the forces right to ensure that it's engaged that lug nut. And there's a phrase, Andy Marchese, who's a scientist at Amazon, taught me, which is, forces are the language of manipulation. And I really like this because it does describe how we operate things in the world. This, of course, led to the DARPA Robotics Challenge. You got the MIT entry there in the video I put for you. The bipedal locomotion got a lot of publicity, but there was actually quite a lot of innovation that happened in the forceful interaction with objects in the environment and the ability to regulate those forces to do useful tasks or semi-useful tasks. My team today is really about industrializing those advances for Amazon's business cases. And so here's this massive field of those storage pods, and we want to be able to put items in and take items out of them using robots. So two big advances, using forces and torques in the control loop to handle high contact, and using AI and machine learning to handle high clutter. Those will be the themes I sort of walk through. So each one of these pods has 4 faces, and each one of those faces has a bunch of these bins. And if we try to use a traditional factory-inspired robotics approach, you're going to take a single snapshot of the bin, you're going to plan a trajectory, and then you're going to follow it as best you can. And the problem is that robots exist in the real world, right? And there are lots of sources of error in the real world. And I don't know if I wanted to tell you, but I'm going to tell you. This is my favorite interview question when I'm asking candidates, is name the sources of error in a robotic system. And I see if they can give me more than one domain or give me realistic errors. But you've got a lot, right? You've got mechanical things like part tolerance, wear, alignment. You've got electrical things like power regulation and switching time, maybe magnetic field variation in your motor and your encoders. You've got control things like bandwidth, overshoot, control authority. You've got software things like latency, discretization. You got a heck of a lot of perception things like calibration, resolution, inference. So all of a sudden, you try and run that trajectory, and smash, you hit the steel frame of the pod, and your robot e-stops, or crack, you damaged the Kindle, or split open a bag of rice inside the bin. And so this is the motivation we need for that new approach. And so here you'll see, some of that work in action. All of these videos are 1x speed. You see we're making contact with the sidewall of that bin before advancing to the next motion in the sequence. So the motion plans are based around anticipation of contact. It's a little harder to see the perception pieces, but I'll show you that later. And then this is out in the real world. So this is at a warehouse in Spokane. We operated these work cells through peak, which is the holiday season. So this was running all through Q4. You can see some of the decision-making algorithms here, like there's space on top, so we're coming in from above. We're modulating that force as we do the sweeping motion. Here there's not space above, so you can see it touch off on the sidewall before it inserts that blade into a very small, very thin opening. If there's a lot of space, we don't bother. We just go as fast as we can. And we're ambidextrous, so right to left, left to right. The system needs to work in all of the different conditions you might find. And of course, it needs to work with all of the different items. So bagged items, flexible items, small items, heavy items. We actually are optimizing for both rate and fullness. So you want to put the biggest item that will fit into that bin. And you want to save the small items for smaller spaces. And if you were to go watch this in Spokane, what you'd see actually is the robot stows a lot to the top couple of rows. Turns out associates don't like to use the ladder. It's slower and you get more tired. And so the robot finds a bunch of space up there. And so it's actually a complementary aspect of how robots and humans can benefit one another. We can take the undesirable portions of the workspace for the associate and let them stow in the ergonomically friendly zones. These are some of our more advanced motion primitives in the lab. This one we call flip up. So we're getting underneath the item. You really don't want to stack items on top of each other. It makes the job of the picker much difficult. The perception team always makes me include this video because they want to show off that they can handle these sort of trickier items for perception. We can stack items, so we have a primitive to put items on top. We do this only when the buildings get super duper duper full, but it's a knob we can turn on and off. And then here you see a remote center of compliance controller. So we're detecting the contact, localizing the contact, and then changing the stiffness matrix of our compliant control to turn a near failure into a success. So again, I'm a little bit of a broken record here, but forces and torques to handle contact in the control loop, which means we have to be running at high rate, a few hundred hertz. And then this inferring available space, this decision-making layer that sits on top of the perception output. These are the tailwinds, and I have a bunch of folks on my team that are working in these two groups. I think this is super cool, but at Amazon, it has to make money. You have to say, so what? And the $1 billion or so that Stow process might be worth is not enough. There's really a much longer vision if I think about this technology. I really think it is new to industrial robotics. So if you have these capabilities and you want to densely put packages into these go-karts that go into the trucks, this is a place where forces and torques and good inference of space is going to be valuable. If you want to win at the game of Tetris of putting as many items into the box as possible, you need these capabilities. And if you want to handle flexible mailers, more environmentally friendly mailers like these paper envelopes, you don't want to rip them. You need to have this sense of force in your machine. Delivery bags, this is what a delivery driver uses. These are actually much fuller than the bookshelves, than those pods in our storage facilities. Here you're at 80 or 90% volumetric utilization. And so you really need to have a good robot if you're ever going to automate this task. And if you think further beyond the next 5 years, if you want to do grocery packing, you're going to break eggs and bruise fruit, right? If you don't have these capabilities. And then in the long term, if you want a robot like Amazon's Astro to operate in a very, very embarrassingly high clutter environment like my basement, especially if those 3 terrorists are hanging around the robot, that robot needs to have a sense of force and a sense of intelligence, right? So this is the long term. I don't want to focus just exclusively on the force control. We also do care about free space motions. And so because rate is so important, we really want to move as fast as possible between the grass pose and the task space manipulation in the bin. So here we've got a couple of approaches that we've been using. Mark Toussaint's out at TU Berlin and has an algorithm called Como. And then we've had collaboration. I've been funding some of Russ's work for a while, and he's done some great things with his students on using convex optimization. I didn't put much else here on the online recovery planners, but as I was talking with Sangbei, I really wanted to bring it up because there are two ways to handle failure. You either have to never fail, you have to make the robot work 1,000,000% of the time, which is kind of what it's like in a welding robot environment. It's really hard to imagine doing that here. Or, second approach is you have to gracefully fail. You have to be able to predict when you're going to have a damage and avoid it, or recover from an emergency stop or some other kind of issue without waiting for a maintenance person to come over to your work cell. And so we're always having these recovery motions. We're always thinking about the non-happy path as we build these systems. And I think that's pretty different sometimes than academic research where you're really just working so hard to get it to work once, at least I was. And for us, we also have to think about all of these edge cases and the long tail of failure and recovery. A couple years ago, we did this big trade. It's still a little bit of like a, you could start a bar fight with this discussion. Impedance control is what we tried first. And we were using robots like Flexiv and Canova, where we had torque control at each joint. And the problems we ran into were we didn't always have a good model of the robot, and we certainly didn't have a good model of the item that we were grasping or its position in the gripper. And we were trying to go really fast. And so we struggled to make this work and eventually switched over to an admittance control strategy, 6 degree of force torque sensor, 6 degree of freedom force torque sensor out as close as possible to the contact location. And we tried this with both UR and an ABB robot that had EtherCAT, streaming to all the joints. And it's probably not ideal, but it's probably much more practical. And so this is the approach that we've been pursuing for the last year or so. The other thing that made this a tractable problem is we're not trying to learn all of the possible motions. If you watch a human stow, sometimes they go in and they do these multi-step kind of Tetris-like amazing bimanual manipulations to fit one extra item into the bin. We just say, we'll never do that. We're only going to take 80% or 70% or 90%, whatever it is, of the stows, and we're going to leave some people there so that they can handle those cases. Instead, we're going to have motion primitives. We're going to try and select between these different strategies that we can develop to be robust. And then the challenge for the decision layer is just which motion do you use and where do you start it? And we have more than 4 now, but these are sort of the major ones. Let me talk a little bit about the perception stack. Same thing here. We really take an iterative approach. This is something I learned in the PhD with Sangbei out at Stanford is like iterative design. If you can move quickly through your first couple of prototypes, you're going to get to a better place than if you stay in analysis paralysis and try and get it perfect in version 1. And so we did the simplest and stupidest stuff you could to start. So we have a pixel-wise occupancy map. We trained a model to do this. It's basically a yellow, not yellow model that runs on the pixels. And that got us started. And we were a small team. We bootstrapped that. We also needed to have masks for the bands. And because there's variability in where these bookshelves are when they show up, a couple of centimeters one way or the other, we need to be able to segment the bins as well, the shelves. We need to make sure we don't think we're going into shelf 1A and accidentally put the blade in on shelf 1B. That does happen, by the way. We progressed from here, so it was pretty quick to move to instance segmentation. So instead of thinking you have just a pile of 1 object, maybe you have a pile of 3 objects. We also worked on getting depth. And so the elastic bands make this a non-trivial problem. So your traditional depth sensors, a LiDAR or projection, a pattern projection kind of system, those elastic bands make it really hard to understand what's in the bin behind them. And so what we did was train a model. We actually started with monocular, so inferring depth from a single RGB camera. It actually worked reasonably well because the structure in the scene is fairly good. It's not like a home where you have every possible variation. We have a pretty well-structured problem, these yellow bookshelves. But we could make it better. And so we used a technique called blind in-painting. Basically, we magic eraser those elastic bands away before we put it into our depth pipeline, and we saw some better results. And then we tried to tackle, this is sort of a parallel problem, not a sequential problem, but yaw and perspective issues. So camera tower is in the center of the bookshelf, and if you're looking out on the edges, it's really hard to tell if the item, think of like a brown cardboard box without a lot of features. Hard to tell if that's a bigger box towards the front or a smaller box towards the back of the bin, whether it's rotated in the bin, in this yaw direction. And so we did some orthographic projection and some other sort of tricks on those outer bins to try and improve performance. We improved our segmentation, so we started with mask RCNN, which already feels like very ancient at this point. And we moved to panoptics. We're labeling every pixel in the scene, labeling things like you can see the red steel frame of the bin, which has a very different stiffness response than the items in the bin or this canvas fabric. And the last thing, at least I'm showing here, is where we got to is learned depth from stereo. So you have more information on, of course, from a stereo pair than the monocular. So we got better performance. Because of those elastic bands and because you have these sort of semi-featureless items like those brown boxes, we did a learned model here instead of a classical stereo approach. And that's performing pretty well. And that's still a single shot approach. We've moved beyond that. There's some cool stuff that is not yet cleared to talk about. But this was the progression, the iteration of our computer vision stack. Now, getting a good depth model, getting a good scene representation is only the starting point. You then have to do something smart with that representation. And so here we've been partnering with a professor at University of Washington, Lillian Ratliff. She's taking a 2-year sabbatical with my team. And we're creating a risk-aware model that's doing this end-to-end matching of items in your waiting to be stowed and the bins that you could potentially stow it into. And we're trying to quantify risk, the likelihood that you'll fail to stow or damage an item. And we're also using exploration. So we intentionally are trying different stows outside of our normal sort of output to get some of this failure cases and improve the performance. So that's that A/B testing that we're talking about. I'm going to shift now. One of my favorite things about robotics is it's full stack, right? So I get to have a hardware team, a software team, motion planning team, computer vision team, decision-making team. And part of your value as a roboticist is knowing which of those domains is going to lead to the best solution or the easiest solution. And often overlooked, I feel like, is hardware. Maybe I'm biased. I came from like building grippers as my background. But I am quite proud of the progression that we've had in our end-of-arm tool. And so we started with very simple paddles, just 3D printed paddles on a 2-finger pinch grasper. And that gave us the pose control, got us started. We moved to having this kind of blade V1. We called it the Fruit Ninja gripper because it was on a rotary solenoid, and so it would, you had to be careful. It would chop fruit if you wanted it to. That had a big sweat volume, and so then V2 we called Wolverine because it would shoot out from behind the paddles. And then in V3 we got the conveyor belts implemented, and now we've really been working on reliability. So we're on like V4.3.2a or something, where we keep tweaking and iterating. Yeah, here's, I guess, the glamour shot. We also do this on the electrical system. And so when we started, we had this enormous dress pack. We had 13 odd cables because we got 4 servo motors. We've got force torque sensors. We've got a couple of limit switches. So we had this, behemoth of a like 2-inch, dress pack that was running down the robot arm and over a force torque sensor at the wrist. So I can tell you how noisy that was when we were flying around with the robot arm. So we'd had some work on creating our own embedded motor controller and put that out on the end-of-arm tool now. And so we're speaking EtherCAT all the way through the system. And now we have a single connector that's basically power and EtherCAT. That's a huge advantage. It also reduced our cost quite significantly. So there's an electrical example of making the robot better. We've also had iteration on the band separation. This system also has a force torque sensor on it. One of the things you didn't think of ahead of time when we started with this 2-jaw design is the bottom jaw would actually pin like a bagged item against the floor. So imagine like a t-shirt inside a plastic bag. You would grab the plastic bag and hold it on the bottom of the bin, and then you'd try and move the pile around. It's kind of like stepping on the tail of the mouse and then like, trying to have it run away. So we iterated and got to this hook design, which is a bit better, and we continue to improve on the motion trajectories. And then I've included a few examples here. These are things our interns worked on. And so we do host interns in my group, a lot of PhD students, but also masters and undergrad occasionally. And so they were coming up with different versions, this little torsion spring linkage system, or this system. I think this was Andy. He was actually out of Aaron Dollar's lab, by the way. We were talking about him earlier. And he was figuring out ways to manipulate not just the elastic bands, but also those bin lips. So you see it's kind of a clunky trajectory, of course, right now, but showing some of the opportunities that intelligent hardware can give you in the band separation domain. And so I think one of the most valuable things I can try to provide you guys is also the set of problems. Having good problems is like having a lot of gold in robotics. And here are some of the things I think are good problems from our side. We still don't have enough bandwidth on the controller. And that's in part because of basic stuff and in part because industrial robots have a bunch of clunkiness around them. Occlusion, this damage prediction, this is very hard. So you're not actually predicting damage. You're predicting sellability. So if you have a box of batteries and you scratch the outside of the box of batteries, you're not going to return it. If you have a collectible Han Solo Golden Platinum Edition, figurine, and that comes with a scratch on it, like you're absolutely, going to be upset and return it. And so you're trying to learn that. High reliability. The life for our system is 10 to 20 million cycles. And so this is not something that you can make out of, paper clips and super glue. And a couple of others there, right? Fleet management, we have 1,000 of our package picking robots in the field. We might have tens of thousands of these robots at scale. OK, so this was kind of the main section. I'm now going to go into the lightning round. So I'm representing one team at Amazon Robotics. There's actually a lot of folks working across projects. So I'll just give you a snapshot of what some of those are and then save some time for questions. So this one is Sparrow. And so this is a tote picking robot. So in this example, it's taking items out of the yellow tote and consolidating them in those gray totes. So there's a lot of the same challenges, a lot of the building blocks you might be able to use, cut across some of these manipulation systems. That's something we think and talk about a lot. What can you reuse? What has to be task specific? Doesn't go that fast. This is that's sped up. One of the problems, this is again talking about that damage. This is our diabolical item set. So this is deconstruction. That's one kind of damage. In the most egregious case, there was like a deck of Magic the Gathering cards, and we picked the top of the box off and then proceeded to pick each card individually out of the box. And so there are some fundamental limits of suction cups, right? They are incredible. They can pick almost everything, but they have these issues. And so my team in Berlin worked on an alternative. You can either detect every box that's not taped down, or you can try a different style of gripper. This video is real time. And so it's using just a simple pinch grasp to singulate these items. Some of the science innovations here is the fusion of multiple cameras to predict not only the the location of these items, but the location of empty space. So when you have a two-fingered gripper, you need to have a volume, an empty volume, where you can insert that lower finger, and that's really hard to do if all you have is a top-down camera. And so I think we did put out a paper on this one. It's fulfilling to watch it go to the end. I still enjoy it. Okay, and then the last example here, this is my team again, but this is my pick team. And so here we are trying to take the items off the shelves. Not only do you have the high contact, high clutter, you also have an ID problem now. You need to make sure we get you the Star Wars Lego set and not the Star Trek Lego set, because that matters. And so to do that, we have a gallery of images, and we're comparing the RGB embeddings of the gallery against the image that we take of the scene. That's a place, actually, these foundation models could make a big difference, so we're investing in looking at that. We also have some innovation, again, on the gripper, so we call this sideways suction. For really thin items, it can be difficult to get a good grasp location, and so we can use the outside of the paddle. And then we have your traditional pinch grasping, so things like coloring books might flop open. We also have some of the video tracking here, so you don't see the CV representation, but we're watching all the items so that if other items start to come out, we can stop the grip or modify our motion in some way to avoid that amnesty event, which is when items fall out of the bins. So I'll wrap up. We do the internships. We also have full-time roles. I'm having a ton of fun there, so I encourage you guys to reach out to me. You can connect with me on LinkedIn, or you can go to the website and look at all the jobs that are open. Some of those are in supply chain and installation and all of that, but we have a lot of jobs in software science and hardware. So thanks so much for the opportunity, and some time for questions.
Yeah, so time for questions.
How are you doing the force control between those two plates? Are you changing based on the item, or is it just like a single feedback force?
Yeah, good question. So we do have a grasp, like a one-off sensor there to detect the force. And it's the same thing we did in an iterative approach. So we started with something we thought was kind of one size fits all. And then as we learned more about item properties in terms of like their weight or their item type, things we can pull out of the catalog, we start to modify that. And so it's not learned, it's just a heuristic, kind of decision tree. But yeah, we choose slightly different forces depending on the item. Yeah.
Thanks.
Mm-hmm.
So a question on the trucks when they arrive. Do you have anything to take? They all come different sizes. I remember when I visited, this was all manual.
Yeah. Trailer unloading and loading is a big open problem in robotics. A lot of companies are going after that one. What Amazon has are sort of human assistance technologies. So we have these like telescoping conveyor things. It's like a French company, I think, that sells them. And so the person doesn't, need to do anything but like kind of pull the stuff onto the conveyors. But we don't have, that's not robotic at this point. Yeah.
Other questions?
You can actually take tours of these warehouses. It is fascinating. Like, you should do it. They just put one in Connecticut that's not far from here. It's maybe an hour or something. Yeah, way more interesting than you think it would be. They're on the website. Like, you can sign up, and then they walk you around, and they show you like, the life of your item from when you order it and how it goes through the. When you work there, you get to do a 3-day tour where you have to do all the jobs, which is like exhausting. It is very hard work. Yeah.
You mentioned that the item size and weight is often wrong. Have you considered using perception to update these values before putting in the bins, and then using those values to also help with item identification and identifying damage or missing parts of an item?
Yep. Great question. And yes, we do. So now, as the item comes into our station, we do have a point cloud of that item, and not only do we use that because it's higher quality data, and also you have articulating items and stuff that can be in different shapes or compressible things. So that data is the data we use. If it's grossly off, we actually go and feed that error back into the catalog to try and heal the underlying data error. Yeah. And then on the other part, in terms of dimensions, so we have done a lot of research on multimodal models, so using weight, text, color, all these other things. Well, color is part of the RGB embeddings, but looking at lots of signals to do that matching. It didn't move the needle as much as I think we were expecting, and so we've fallen back just on RGB embeddings at this point, but I think there's opportunity for some of those signals. Depends on whether you have that data or not. I think maybe some of the problem was that data wasn't always great, and so it could actually be a bigger problem for the model than just the gallery images. Even the gallery images are flawed sometimes. You get the Christmas packaging of the toothpaste that looks very different than the Valentine's Day packaging of the toothpaste, and you have to adapt to this. Yeah.
Hey, we've been promised, the controls guys have promised us virtual impedance for years.
Uh-huh.
So what's the deal? I mean, just given your recent experience, where do you think the gap is?
Yeah. I mean, for us, I think part of it is if you're trying to sense at just the joints, you have a physics problem that if the contact is way out at your fingertip, you really are not relying on your shoulder torque to sense. I think this is one of the problems. I think having that model is the other big one, and I don't know, why can't we solve those? I don't know. We are very practical. So Amazon Robotics, industry in general, you care about getting something that works more than you care about advancing your technology. And so Jeff Bezos has this great quote, which is you have to be stubborn about the problems you're trying to solve, or you'll give up too soon. You have to be flexible about how you solve them, or you'll never find the right answer. I always oh yeah, that was a good Jeffism. Yeah. And that's not a good answer, but yeah.
So when you mentioned that there are 100 million different objects that you might need to pick, so how do you develop metrics to know whether a new change is going to help or hurt? Mm-hmm. Because I imagine there's a long tail of edge cases. So do you use simulation at all, or do you actually deploy things and then evaluate?
Yeah, the strategy you can use now, which is, I would not claim to be the best strategy, but once you mess it up 3 times, you sort of exclusion list it. And so it's more of you have to pay for it after you've damaged it 3 times, this kind of thing. You can try and learn this, right? So we have a lot of attributes for those items. So we may not have full 3D CAD models, but we know, usually if it's a bagged item or a boxed item or a cylindrical item or this kind of thing. But we do kind of keep that exclusion list running to try and avoid those cases. The other thing here is the distribution is not even. We sell way, way, way more AA batteries than we sell, size 10XL, whatever. And so you have this very strong, if you can handle the first 100,000 items we sell, you're handling some large percentage of sales, if that makes sense. So we bias towards those. Yeah.
So Aaron, maybe a hot take question, which is not technical. So we've been hearing in robotics a lot about humanoids and foundation models.
Yeah.
I'm wondering what your takes are on those things in context of these warehouses.
Yeah. I will only give you my opinion, right? So Amazon has invested in some of these technologies. I am not, like, they don't consult me necessarily on those traces, but I'll give you like my very local opinion. I'm very excited about foundation models for computer vision, for the perception stack. And also for like flow in the building, right? You have this system of system, multivariable optimization kind of problem. And I think those techniques can have a lot of power in that decision-making world. I am skeptical that they can overcome friction and like the physical world. And so, you know, TBD, like I'm not right. This is the skeptical is the right term. But I think their first use cases are in the perception stack. On the question of humanoids, I freaking love humanoids. As a guy who likes robotics, if the floor is flat and concrete, it does not necessarily like match my expectation of the mobility system that you would choose for that floor. So if we're hiking a mountain or, you know, descending that canyon on Mars or whatever, I think I'm very interested in legged robotics. If I'm trying to drive, you know, from here to the table, like wheels are a pretty dang good solution. I mean, this kind of gets also to like, I showed up at Amazon, they're like, oh, so are we gonna use gecko adhesives everywhere? I was like, well, I love geckos, but it's pretty hard to beat a suction cup, you know? It's pretty hard to beat duct tape. And so I think you gotta work backwards from the application and use humanoids where humanoids make sense and use wheels where wheels make sense and use fixed mount robots where the robot doesn't need to move, right? Yeah.
Is there a world where you maybe start making modifications to the shelves as well? Because
yeah.
I'm not going to lie, those elastic bands seem like a particularly difficult thing to manipulate, and
Yep.
were probably designed with like human manipulation in mind when they were first
Yeah, of course.
designed, like 20 years ago or something.
Yeah.
Maybe. So
100%. There is a world, and in fact, there's another team that's taking that sort of blank slate approach, and they're looking at containerized storage. And so they're actually using totes as opposed to those fabric work cells because they're much more they're much easier for robots to manipulate. And so we kind of have this dual development approach happening at Amazon. And the problem is there are 5 million of those pods already out in the buildings, and so it's very expensive. Even the elastic bands, they're $1 or whatever they are, 50 cents. But if you want to go change all of them, you need to change 5 million times maybe 200 per pod. And so that's made me be very hesitant to try and take those, to cut those corners or make the problem easier. But if you're building a new building, we call that a green field as opposed to a brown field. Yeah, we are absolutely trying to make things more friendly for automation. Yeah.
I had a quick question. It's hard to tell from the video. When you shoot the paddle sort of into one of those cubbies, you push it over. Is there a box in hand ready to go? In other words, is your perception able to tell before moving it over the available
Yes.
volume?
Yeah, this is the hard decision-making problem. That's that like inferring potentially available space. Yeah, so we already have the item in the hand, and then the paddle shoots out while we're still gripping the item. And so if we don't make enough space, now we've got to go put that item back, which is not as bad as breaking the iPhone, but it costs you 20 seconds. And when we're trying to get hundreds of units per hour, you can't do that too often.
And that perception's pretty accurate as to, in a cluttered box as opposed to one shuffled to the side, how much volume is available?
I would say, 2022 me would say it's pretty accurate. 2024 me, definitely, my team watches this, they need to keep working. Let me put it this way, like a person can still find more space than the perception system can find, right? So we clearly have not gotten where we could get to. Yeah.
I love all the questions. Maybe last one. Last one.
So in answering the humanoid question, you answered about the feet.
Mm-hmm.
What about the hands?
Yeah, great follow on. I love dexterous multi-fingered hands, but they're really hard to make reliable. And they were made to be a generalist, right? And so I think, I don't know what the right answer is here either, but there are sort of very simple hands where you try and put all the intelligence in the brain, in the sort of control or the, and that's the two-finger, kind of pinch grasp hands. You can actually do a lot. You saw us, singulate that. Then there are task-specific end-of-arm tools. So if you go to a assembly line, you'll see these incredibly, individualized hands for, doing a specific step in the assembly of an iPhone or something. And ours is kind of like that, because we stow all day for 22 hours. That's the only thing we need to do. We don't need to go, cook dinner or, change a diaper. And so we can make it very task-specific. And then I think if you want to be in a home or you want to be in an environment where you got to do lots of different tasks, that's the place for multi-fingered or dexterous hands. That's just not our place. Our place is this specific, it's somewhere halfway between the welding robot and the in-home robot, right? Like we have structure, but within that structure, we have a lot of variability in the items and the pose and all of those things. Yeah, so I think it's definitely not the right solution for me, but for some of those longer term general or manipulation applications, yeah, and I love them, right? Like as a mechanical engineer, I love finger design. I love thinking of all of the tactile sensors we can put at all the fingertips and along all the joints. So keep building them, right? If you're working on them, keep building them. But I probably won't be buying them for this.
Great. I know there are more questions, but we are over time, so we are going to cut it off, and we can come ask the questions after we cut it off.
Yeah.
So let's thank Aaron once again for the wonderful talk. Yeah. And now the floor is, yours to ask more questions if you want.